All right, so the next thing we want to talk about is a notion of propositional equivalence. When are two propositions equivalent to each other? I've used the equivalence symbol, the triple equals, previously when dealing with like combining constants together. I did it with the examples when I was talking about precedence, like the order of operations. But let's look at a definition of exactly what this equivalence means. So two propositions A and B are equivalent if the biconditional A if and only if B is always true, regardless of the truth values of A and B individually. So remember that, pull this up again, remember that biconditional is true exactly when the P and the Q have the same truth value. So if P and Q are both true, it's true. And the other situation when it's true is when P and Q are both false. So if the biconditional A if and only if B is always true, regardless of the truth values of A and B individually, then it means that A and B must always have the same truth values, either both true or both false. That's what makes them equivalent. So let's look at one example. Okay, it's going to get a little bit meta here. The biconditional statement itself, P if and only if Q, is equivalent to saying P implies Q and Q implies P. Now, this equivalence here is basically justified just by the meaning of biconditional. This is what, like, you can think of this as a definition of if and only if. Okay, in fact, it's even in the words P if Q and P only if Q. That's actually one of the ways to say an implication is only if. It kind of reverses the arrow. So P only if Q means Q implies P. So it's if and only if. It's right in the definition. Okay, it's like saying we have the implication one direction and the other direction. So this is an equivalence. Now another equivalence that I think would be interesting to look at comes from this table. Okay, you can prove equivalences by looking at a truth table. So let's examine this column and this column. Look at those for a second. Do you notice anything? Yeah, in fact, they are the exact opposite truth values, right? False, true, true, false, true, false, false, true, right? They're exact opposites of one another. We have a name for that. It's called negation, right? So what we're looking at here is the column for exclusive disjunction, so XOR, and then the if and only if. So if they're the exact opposites, then we could actually say that P if and only if Q is equivalent to the negation of P XOR Q. And that is true. That's an equivalence. Okay. So now let's look at the XOR. So P XOR Q. There's actually another equivalence we can set up for P XOR Q that comes again from essentially its definition. Remember, exclusive OR is like P or Q, but not both, right? And so if we want to write that, we could write P or Q, and then the word but in English is essentially the same as and, all right, logically. I mean, it has a different connotation because it sort of sets up a negation. It's like but, it's like sort of and, not this. It sets up an expectation that there's going to be a not coming right after it. But logically, the word but is equivalent, like the same as and. So when we say P or Q but not both, it's like saying and not both. And both would be P and Q. Okay, so this is literally P or Q and not P and Q, not both, right? So this is essentially, by definition, what XOR is saying. So that is another valid equivalence. And then, having sort of set up these equivalences, we can put them together to say that since P, if and only if Q is equivalent to this, that must also be therefore equivalent to the negation of P XOR Q, and the P XOR Q can be replaced by this statement, and we could write P implies Q and Q implies P. It's actually equivalent to the negation of P or Q and not P and Q. And so the point I want to make here is just that the equivalence is what's called a transitive relation. You can say if A is equivalent to B and B is equivalent to C, then A is equivalent to C. And so you can use it to make substitutions, and you can, from equivalences, you can combine them to make new equivalences. It's just like working with algebraic equations, pretty much. Actually, algebraic equations is not quite the right idea, maybe more so like algebraic identities. A better analogy would be like identities, like you did, like the commutative law and the associative law and the distributive law. Or in trigonometry, you have things like, the double angle identity and the Pythagorean identity and the quotient and reciprocal identities. So these equivalences are like identities. In fact, they are identities for logic. Now, this is, by the way, not a particularly useful identity or equivalence. I just kind of put it together as an example of how you can combine them. Right? We're going to go over a lot more useful equivalences in a future video.